Welcome back. We are continuing to study the topic of exponentials and logs. The purpose of this video is to specifically talk about how we can evaluate log expressions and how we can then solve log equations. As a brief reminder, I have a pictorial of a typical logarithmic function. As you can see, we have the equation y equals the log of x to the base b. Again, the base is b. We do have some criteria that have to be met. It's just some number, but it does have to be greater than 0 and it cannot be 1. Where you see the x here, that's actually called the argument of the log. And as discussed in some previous videos, that argument has to be greater than 0. In other words, it has to be a positive quantity, cannot be negative, cannot be 0. And because of that, depending on what algebraic expression is actually captured here, the function likely has domain restrictions. There are some unique examples based on an algebraic expression there where perhaps it doesn't, but we do need to think about domain restrictions. For example, for this basic log function, there's a reason that we don't see any portion of the graph on the other side of the y-axis, and it's because the x's have to be positive. We're not allowed to have negative x's. Okay, so back to the point of this video. The first thing I want to cover is evaluating log expressions, and then we'll move into actually solving equations. So when you think about evaluating log expressions, there's two different topics I want to cover. Number one, as we do the evaluation, can we use a calculator or not? And that may depend on specific directions from an instructor per se. So this top portion, I'm going to be talking about how you can evaluate a log expression without using a calculator. And then down here, we'll do a couple of quick examples where we use a calculator. Okay. Without using a calculator, there's an inherent implication there that if we cannot use a calculator, then one of two situations, or perhaps both of them combined, are usually present in that problem. Number one, there's probably some log rules that are sitting there. The question is do we see them or not? The better you get at identifying those log rules, the more quickly you'll be able to address these problems. The other possibility is that maybe you're given some additional information along with the request to do an evaluation, and it could be both of these as well. So let's get into the examples. The first one that I have here just says, please go evaluate this. We have 1/2 times the log of 64 to the base 4. Sometimes you might also see it written like this. Maybe somebody will give you a problem and say, hey, find x. This isn't really a logarithmic equation because the x isn't embedded in the log. They're just really asking you to please go evaluate that and let's call it x. So again, we're doing this without a calculator. That means that there must be some log rules present here. And in previous videos, we talked about if you have a log expression, if you have your base and your argument, there's a great simplification tool you can use. If you can get the argument to be the base to a power. And what I mean by that is, can we rewrite 64 as 4 to a power? If we can do that, it's going to allow us to use a pretty slick log rule. So I'm just going to begin by rewriting this here. So I have 1/2 times the log of base 4. And if you haven't figured it out already, 64 can actually be written as 4 cubed. If you're not sure about that, you could get your calculator out and just start checking things. What is 4 squared? What is 4 cubed? What is 4 to the 4th? And see if you can find one that matches 64. Now that we've identified how to write 64 as 4 to a power, we get to use that log rule where we can take that power that is in that argument and we can drop it down into the front of that log. And so what we have now is 1/2 times 3, that piece that I moved down there, and then we have times the log of 4 to the base 4. Now, if you remember, this is another log rule. When the base and the argument match, this actually is just 1. So what this problem actually simplifies to is 1/2 times 3, and then we have our 1 here, which if we do that, we simply get 3/2. And so although this looks a little intimidating, that actually is just a number, believe it or not, and it is the number 3/2. So this is an example of how we can evaluate a log expression without using a calculator and using our knowledge of log rules. Okay, this second example is worded a little differently. It says, given that. So I'm going to give you some extra information, and then I want you to find something. So this is a great example of a problem that uses both of these. There's probably some log rules in there I'm going to need to dig out, and I've given some additional information. So again, it says, given that the log of 3 base 2 equals 1.585, and that's rounded, and that the log of 5 base 2 equals 2.322, please go find this. And it's the log of 15 to the 4th power to the base of 2. Well, one thing we can note right away is that same rule we used in the previous problem. If we have a base to a power, the argument has a power in it, we can drop that down in front. And so I'm going to rewrite this as 4 times the log of 15 to the base of 2. So now the question is since they provided me this information, it must be useful or necessary for something. And this takes a little bit of practice to start to identify the use of these log rules. But if you remember, there's a rule that talks about expanding or condensing a log. So typically when you have a problem like this, they're trying to get you to look at this number here, the 15, and ask yourself, is there a way we could arithmetically manipulate this to write it in a form that involves a 3 and a 5? Maybe I can divide it or add it or subtract it or multiply it, who knows. In this case, if you think about 15 is actually 3 times 5. So if I want to rewrite this, I could actually think of 15 as 3 times 5. And now, because I have the log of 2 pieces multiplied together, I can actually use the log rule where I'm going to expand this into 2 separate logs. So if I do that, I have 4. I'm going to use a bracket here because that 4 does multiply this whole thing, so I want to be careful of that. But if I break this into 2 logs, I have the log of 3 plus the log of 5, And so if you remember that log rule, when you have a single log and you have multiple expressions inside that are either multiplied or divided, we can break it into multiple logs. And since these are both multiplied, we end up with plus signs because they're both up top. So now, hopefully these look familiar. These are the values that you were given in the problem. And so if we stick those in there, we actually just have a big addition problem that we're going to do. So the log of 3 base 2, that is 1.585, and log 5 base 2 is 2.322. So the last remaining step is to add these together and then multiply it by 4, which I would do in my calculator. And when we do that, we get 15.628 as the answer. Now, if you had wanted to check your work, you could have taken this in the beginning, and you could have actually put this in your calculator using the change of base functionality, and you would have found that you would have gotten the same answer. Now, their intention wasn't to have you do that in the calculator. They wanted you to use this information, and so this would be the proper way to do that problem. Okay, so these are examples of doing some evaluations without a calculator. Now, there may be problems that you're given and you're asked to use a calculator. This is a example problem that I actually covered in a previous video where we can use our calculator and use the change of base functionality. If you remember, calculators have a log and a natural log ln button, and if we want to use that functionality in our calculator, we could change this problem into a base 10 or a base e. I'll show the base 10 here. If you cannot remember this, I encourage you to go back and watch the video that talks about change of base. But if I switch this into the log of 7 base 10 divided by the log of 5 base 10, I can then put that in my calculator and evaluate that pretty simply. So this happens to be a Casio. Some of you may also use the TI. If you remember, turn this on, and here's the log base 10 button and the natural log button. So I did base 10, so that's the one that I'm going to use. So I need to do the log of 7 divided by the log of 5. So log, if you remember, it's going to give you that parentheses right there. So the log of 7, I need to close the parentheses, and I'm going to divide that by the log of 5, closing my parentheses again. And I get 1.20906. Typically, when you're asked to do a problem like this, they'll tell you how many decimals to round it to. So let's say maybe we had wanted 3 decimals, and we would stop right there. 1.209. Okay, so pretty straightforward change of base problem using a calculator. And again, if you're struggling with this concept, I encourage you to go watch the other video that does multiple examples of this. Okay, so what about something like this other example over here? Maybe this is an answer that you got after you've solved some type of equation, and this is what would be called an exact answer, but maybe your instructor wants you to answer it using decimals instead. So you need to know how to put this into a calculator. You want to be really careful whenever you have a fraction with logs that you protect, that numerator and protect that denominator. So to start, this is a natural log. These are both natural logs. So I'm going to be using the ln button on my calculator. First, I'm going to enter that numerator, which is the natural log of 3. Again, they gave me the parentheses, so I'm going to close out that parenthesis. Now, this is where you really want to be careful. I'm going to divide by this entire numerator. And even though I don't have it written that way here, I'm going to put some protective parentheses up there to remind myself that anytime you have a denominator that's complex in terms of you've got more than one term that's either added or subtracted together, you really want to protect it with parentheses when you put it in your calculator, or your calculator is not going to do what you think you told it to do. So to enter this denominator, I'm going to enter a parenthesis so I can protect that, and then I'm going to do 1 plus. Now I have 2, so 2, and then times the natural log. Again, it gave me the parenthesis for the 4, so I'm going to put a 4 there. Now I need to close that parenthesis out for the 4, and then I'm going to also close out that parenthesis to close out the denominator. And so if I hit enter, I find out that this equals 0.291. And again, your instructor will likely give you the number of decimals they would want your answer to, whether that's 3 or 4. Those are pretty typical. Okay, so these are examples of solving, evaluating log expressions. Okay, now the other piece is solving log equations. And there's some similar terminology here that you may have learned if you've already learned how to solve exponential equations. And what it is there's 2 primary methods for solving log equations. We have the one-to-one property method and the inverse property method, similar to what we saw when we solved, again, those exponential equations. The key, again, for a log equation is that variable that we're trying to isolate, that we're trying to solve for, it is embedded inside of a log. So it's in that argument. And so again, we have the variable that we're trying to solve for. It's embedded in the argument of the log. We need to get it out of there. We will not figure out what x is unless we get it out of that argument of the log. And there's 2 ways to do that: one-to-one and inverse property. And just as you may have suspected, the one-to-one method is the simplest, easiest, most straightforward if it's one-to-one. If it's not one-to-one, we're going to do it the other way using the inverse property, or what I like to call the long way. And so the long way means we have a log. It is not one-to-one, and so the inverse property says I'm actually going to turn it into an exponential instead. So I have a simple example of each one of these that is very straightforward, and then I will have a subsequent video that does a few more examples if you feel like you need some extra practice. These are pretty straightforward examples, and so I would encourage you to also watch the second video that has some examples that are a little bit more challenging. Okay, so the first example, this is an example of something that's one-to-one, because what does that mean? If it's a one-to-one problem, it means you're going to have a log equals a log. Okay, that's it. You don't see anything else there. A log equals a log. They have to both be to the same base. And if that's the case, you get to take those arguments and just pull them outside and set them equal to each other, similar to an approach we used on the exponential problems. So if you look at this example, it's definitely one-to-one. I see a log equals a log. They both happen to be base 10. If you remember, when you don't see a base written there, it's because it's a 10. And so because this is one-to-one, I can grab these arguments and simply pull them out and set them equal to each other. Okay, so that is going to be x squared equals 6 minus x. Now this, if you remember your algebra skills, this is actually a quadratic. So I'm going to set it up like a quadratic, which means we want to set it equal to 0. So I'm going to have to add x to both sides and subtract 6. When I do that, I can rewrite that quadratic equation like this. Again, if you need to brush up on your factoring skills, you may want to go do that. But typically in these log problems, if you end up with a quadratic, a lot of times they do factor. They're not trying to give you the most difficult quadratic to solve. So they typically do factor. On a rare occasion, maybe they won't, and you'd have to go use the quadratic formula, but try to factor it because most of them do. Okay, so if I factor this, I have x and x. A 2 and a 3 will be what I will use to get the 6, and then the 3 will be positive and the 2 will be negative. If you're not sure if this is correct, you can fold it back together to confirm. Now I can use that zero product property again and solve each of these problems one at a time. This one results in x equals 2. This one results in x equals negative 3. Now, this is where you have to be very, very careful. You are not allowed to stop here. And that gets back at this concept up above where log equations can have domain restrictions. And so we really need to make sure that these solutions that we just found are legal. If they're not, we have to cross them off. They won't work. Now, you could have a log equation where you get more than one answer and they both work. Maybe one works and one doesn't. Maybe neither of them work. And if nothing works, you'd say you actually have no solution. So how do you check these? Number one, you have to check each solution one at a time. You do that by taking the value that you obtained for x and you plug it back into the original equation in any argument that it shows up in. And so I'm going to have to take this 2 and put it here and here. And what you're checking is that this value here, this argument, it has to be positive. And as long as it's positive in each argument, you're okay, and that solution works. If you fail in just one spot, you're done and you would cross it off. So I can see that if I put a 2 here, 2 times 2 is 4, that's positive, so we're good there. And if I put the 2 here, 6 minus 2, that's 4. Again, we're positive, so I'm good. So this solution works. Now let's try the negative 3. If I take a negative 3 and stick it in, if I square a negative 3, that's a positive 9. So that's fine, that's a positive value. And now let's try it over here in the second spot. I would have 6 minus that negative 3. 6 minus a negative 3 is actually 6 plus 3, and I get a 9. Again, that's positive, so I'm good here. So this example happens to have 2 solutions, and they both work. So I would capture both of those as an answer. Okay, not all log problems are one-to-one. In other words, they don't look like this. So here's an example of an inverse property problem. So again, we have a typical log. Y equals the log of x to the base b. If it's not one-to-one, which this clearly isn't, we want to switch it into its exponential counterpart. That's how we're going to get that argument, that x we're trying to hunt down. That's how we're going to pull it out of the log. So if you remember, if you want to rewrite to exponential form, you take the argument and you write it by itself, and then equals the base of the log becomes the base of the exponential, and this number that was over here by itself, that actually becomes your exponent. So if you're not feeling confident yet going back and forth between log and exponential form, you may want to practice that. And again, there's another video discussing the log rules that has some examples of that. Okay, so if I look at this example, this is not one-to-one. I do not have a log equals a log. And so I'm going to use the inverse property. Now, I can't use the inverse property until I do have a single log equals a number. And this one was already set up that way. In the other video I'm going to do, that won't be the case. So we'll have to do some manipulation first. But this is ready to go to write it as an exponential. So if you recall, we're going to take that argument, which is x equals 1, set it equal to the base. Well, what's the base? Well, it's not written, but if you remember, anytime we have the natural log, it's because the base is e. If you can't see that, you may want to write it in to help yourself out. So the argument equals the base, and that becomes your power. So this is my new algebraic expression, x plus 1 equals e cubed, and I need to solve this for x. So pretty straightforward, I can just subtract 1. So x actually is going to equal e cubed minus 1. And so that is my answer. There isn't any additional simplification I can do here. This is called an exact answer, okay? Anytime you're representing an answer and you have maybe an exponential using the e or a log, those are called exact answers. If your instructor wants you to, they can ask you to report this as a decimal answer instead, which would require you to get your calculator out. So again, here on the Casio, I'm going to need to know where that E button is, because this is E cubed. So each scientific calculator does have an E button, and a lot of times it's above the natural log button. On the Texas Instrument, that would be the same. So here's the log, the natural log button, and that e to a power is right above it. And so because that e to a power is above the natural log, I'm going to have to use my shift or my second key. So I'm going to hit shift and then go right there. And you can see I have the e, and it's asking me what power do you want to put in there. So I'm going to put the cube in there. So I have e cubed, and then I want to subtract 1 from that. So this is the exact expression I'm asking my calculator to do. And if I hit enter, that is what I get, 19.085. And actually, if my instructor wanted me to round it to 3 decimals, because the digit to the right is 5 or bigger, I would round that up to a 6. And again, pay attention. Anytime your instructor asks for a decimal answer, they'll probably tell you how many decimal positions they want, whether that's 3 or 4. Those are pretty typical. Okay, so these are 2 examples of solving log equations. Again, we have the one-to-one method and we have the inverse property method. These were both pretty straightforward examples, so I do have an additional video I'll be posting right after this one that goes through some examples that are a little bit more complicated, and hopefully those will help you out.